Okay, now let's actually do distributed constraint satisfaction. So we're gonna be talking about the filtering algorithm, which is sort of the most obvious first algorithm you can use. This is the algorithm in the textbook. So the filtering algorithm, a couple of things I want to talk about first is that this is a message passing algorithm. Like all algorithms in most algorithms in multi-agent systems, you have agents sending messages to each other. So I'm going to use a very simple example of a graph coloring problem with these three guys right here, three nodes, and we'll call them x1, x2, x3. In this distributed solution in the filtering algorithm, like in many, each agent is a node, and they'll all operate, independently in parallel, if you will. So x1 is an agent, and x1 also owns variable x1, so he can change its color. And x1, the same for these two guys. And think of these as machines. They're sending messages, say, over the internet, and each one owns a particular variable, and that's it, right? So they can talk to each other, but this guy cannot change x1 value and vice versa. And so that's pretty standard. There's many different ways to make a problem distributed, right? You have variables, and maybe one machine can own two variables, but this is pretty standard, one variable per machine. Okay, filtering. How does it work? So the basic idea is each one of these guys has a table. So x1 is going to have a table here, and it's going to be a table over all its neighbors, in this case x1, x2, and x3. And so those are the rows, and the columns are the colors, right? So I'm going to say, this is blue and blue, red. So these are the possible colors that the nodes can be, also known as, the domain of the variable. So blue, red, and green, and x1. So this is saying x1 could be blue or red or green, and x2 could be blue, red, or green, and so forth. And what he's going to do is he's going to cross these out as they become impossible, right? So we can say, I don't know, let's say that, to start with, for whatever reason, these are all checked, right? So x1 starts out with this table, actually. So this table tells x1 that, I can be any color, right? They're all free to me. But x2, he can only be red or green, and x3, basically he's down to just red, right? X can only be red. So there we go. And then, these guys, x1, x3, similarly will have a table like that. Or maybe not. Maybe it's different. It doesn't, it depends on how the problem is set up. So, okay, go back to the algorithm. The revise method is the heart of the algorithm. So basically, what you're going to do is, let's look up here in the filtering method. Each agent is going to run this filtering method, and he's going to say, for all my neighbors, for each one of my neighbors, J, I'm going to revise I is me, so I is me, the agent. I'm going to do a revise of me against J, each one of my neighbors. So I'm going to apply revise of me. In this case, agent 1, x1, is going to do revise of x1, x3, and revise of x1, x2. That's what it's saying. And so here's revise of x1 and x3. And what this does is basically, the agent I sets himself to one of his possible colors, in turn. So this is a for loop. I'm going to be red, green, and blue. And then given that I am, say, red, we go here. If there is no way that agent J is consistent, so I'm doing 1 and 3, say, so there's no way that AJ can find a color, then I'm going to remove that color from my domain. When I'm done, then, if my domain has changed, right, my old domain is not equal to my new domain, then I'm going to tell people, hey, handle this. So basically, I'm just going to tell people about my new reduced domain. And then they are going to, because of that, they're going to call revise again, Okay, so let's look at that. So let's say the first thing x1 does is, he's going to check all his 3 colors. He's going to do revise agent x1. Remember, we're doing x1 revise x1 x3. Right? So that means that agent x1 is going to first set himself to blue, temporarily. It's like, okay, if I was blue, can x3 find a color? Yes, because x3 could be red, right? If I am blue and x3 is red, that works out okay. So that's awesome. If I were red, is there a color for x3? Well, no, actually, because if I am red, x3 cannot be red, but x3 can't be blue or green, so x3 is hosed in that situation. So that's not going to work. So at that point, that's when x1 is like, wait a minute, I gotta redo, I can't be red. So he's gonna add that, right? x1 is gonna add this cross here, and then later on, green is gonna work out fine. So he's gonna check green, but green works out fine. So then x1 is gonna end, and he's gonna say, wait a minute. He's gonna tell blue, so he's gonna send this message to blue, which you saw here is called the handle new domain message. And in that message, what we have is that basically he's gonna send blue that new domain that says x1 can be blue, red, but not red and green. So he's gonna send them, that row of his constraint table, and then x3 is going to add that row to his constraint table, right? So that's what's going to happen, similarly, let me just do another more step. X2 could have done the same thing, right? So x2 could have done the same revision method. He could have figured out that, hey, I cannot be red because of x3. So let's say, imagine that x2 did a revise between x2 and x3. x2 figures out, I cannot be red. So x2 goes ahead and sends the message to x1 like, you already knew I cannot be blue, but here, check this out, I cannot be red either. So he sends that message to x1. x1 adds that message to himself right here. And now he goes again and does a revise of x1 and x2, and he realizes that, if I am blue, if I am blue, it's okay. If I am green, so agent 1 is like, okay, if I am green, well, x2 has to be green. He has no other choice, so that's not going to work. So therefore, clearly, I cannot be green. So if I am green, x2 is green, I have to cross that out, and bingo. Now I have a solution because I know, hey, I can only be blue, x2 can only be green, and x3 can only be red. So that's how the filtering algorithm works. Now, the main thing to note is that, here we found a solution. The filtering algorithm will stop before finding a solution. In fact, almost always. So it stops before finding a solution because all it does is before finding solution, because it only goes down to one solution when the problem is like super constrained, like really constrained. So there's only one possible solution in most cases. I guess in most cases, yes. In constraint satisfaction, there are multiple solutions, and in those cases, the filtering algorithm, all it does is it reduces some of these domains, to smaller, but it's still, you end up with a table with, some crosses there, but still plenty of open spots. And, that doesn't mean that the remaining open spots are all solutions, right? So those are still, some of those combinations might not work, actually. So filtering algorithm is a good sort of first step to reduce, all impossibilities. So it reduces the domain, but it doesn't actually find a solution most of the time. It will just eliminate impossibilities and reduce your domain and get you to a point where you can then do a more straightforward search. So, for example, yeah, another problem is that it will not find an impossible. If you have a problem like, oops, like the following, um, again, the same problem, but now only two colors. So you have the same problem, but anybody could be, say blue or red. Um, any one of these can be blue or red. Well, if you have two colors and these three nodes, you hopefully know, you can see that there is no possible solution, right? So there is no possible solution to color this graph with just two colors, right? You got to have blue, 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 red, but the revised algorithm will not tell us that no solution can be found. So sorry, the filtering algorithm. So the filtering algorithm will not find no solution. So it does not tell us there is no solution possible in this example, and in similar other examples. So that's another problem, right? So sometimes it will tell us there is no solution, but sometimes there is no solution, and filtering does not tell us that there is no solution, which is a problem. And the reason why is because the filtering algorithm, the revised function, has two arguments, x1 and x2, and basically that's the problem, because it only checks that two guys are consistent. It doesn't check like three guys are consistent with each other, and that's how we can solve it, which we'll show in the next video.